Welcome and hello. This is a HEC RAS controller exercise called flow results versus Culvert size. So what we're going to do is create a HEC RAS model and have a few different alternatives and then compare the results for those alternatives, specifically the water surface elevation, the depth, velocity, and the Froude number. So what I have on the screen here is my HEC RAS. We're using version 6.6. Let's get started. I'm going to go up to File, New Project, and then navigate to where I want to save this project. Okay. In this directory, we'll call it project 2. This project 1 was my prep. And okay. It's just telling me that it's set to the US customary units by default. That's okay for now, but I actually want to be using metric units for this exercise. So go up to Option, Unit System, and then click on System International, Metric System. Okay. And it's okay. Open geometric data. I'm going to start sketching in a river reach now. So just do some single left clicks and double click at the end of the river reach. I'm going to call this river A, reach 1, and okay. Click on the cross section editor here, and then options, add new cross section. I'm going to start with the cross section at the bottom of the reach. So I'll type in 0 for the river station number. And then for the station and elevation data, this is what I had copied onto my clipboard and prepared. So I just paste those values in right there. I'm going to type in 0, and then the Manning's value, I'll just type in 0.04. And then let's see, I'll just say the entire cross section is the main channel. So 0 and 28 meters, apply data. Over here on the right is the preview of the cross section. So I'm going to add a few more cross sections. That was at River Station 0. I'm going to go Options, copy the current cross section. Instead of River Station 0, let's go 300 meters. And then what I'm going to do is type in 300, of course, for the distance to the next downstream cross section. And I'm also going to increase the elevation. We'll say 3 meters. So that would be a 1% slope. So type in a 3, click OK. These numbers all increase by 3 and apply data. So I can look at the profile plot if I wanted to just confirm that I do have a positive of 1% slope between my two cross sections. I'm also going to add a few intermediate cross sections as well, then add the culvert. Then we'll continue on with the flow data, simulation, and the results. We'll look at those results here in the graphical user interface. Then after that, we'll fire up the RAS controller code and compare the results so I can demonstrate how to use the libraries in the RAS controller to retrieve the same results. Okay, so where were we? We need to add the cross-section interpolation within a reach. It's going to be for this entire reach here. Let's go every 50 meters, interpolate, and close. Now I propose we add our inline structure and culvert to River Station 100, or let's make it 95, so just downstream of River Station 100. That cross-section at River Station 100 will probably be the one that we want to use to compare the results. All right, so let's see. Inline structure, and then add an inline structure. Well, what did I say? 95? That 95 will be the upstream face of this inline structure. That is in place. And then let's click on Weir Embankment. For distance, we'll say 5 is the distance from the upstream edge of the inline structure to the next cross section. So 100 minus 95 is my 5. We'll say 10 meters, for instance. And then the station, I'll just put it at 86. So that should be the top of the embankment for the very end, left and right ends of the cross section. So 0, 28, that's the total width in meters, 86, 86. We'll say there's no side slope, so it's just vertical, and then click OK. All right, so there's that. Here's the 86 I was talking about. All right, so let's close that. We can see right down here in our, okay, hold on a second. I'm just going to modify the plot schematics to allow me to pan around a little bit easier. I'm not sure what other people do to do this. I mean, this is not a geo-referenced model anyway, so this is just kind of a hack. All right, so there is the inline structure. Flow is going downstream, down on the screen from this view. And what we want to do next is save this geometry, and I'm going to call it the no culvert geometry, but then I'm going to create a culvert. That'll be alternative 1, and then alternative 2 and alternative 3 will be the 3 different combinations of culverts and barrels that I'm going to use. So this right here is what I have. I'm going to have three different alternatives, and we're going to have a certain number of barrels at a certain size using a constant invert of, let me see, cross section. Let's go with, okay, this is the wrong cross section. I want to go River Station 100, which is right here. Let's go with an invert of 81. 81 would be close enough for our invert. In fact, let me go ahead and get the Excel started up. So here is Excel. We're going to need this later on anyway to write our HEC RAS controller code. So the first thing I do when I open Excel is I'm going to go to Options and then make sure that I have my developer checkbox, my tab enabled. So Customize Ribbon. I already have it checked. So go ahead and check that on. Click OK. From the other Excel file, I had that saved onto my clipboard. Here is that text. Let me just kind of reformat things here. So I have my three different alternatives, 1, 2, and 3. Alternative 1 is going to have one barrel that's 3 meters in diameter. Alternative 2 is going to have two barrels, both 2.5 meters in diameter. And then alternative 3 will have three separate culvert barrels, all at the same invert, all the same properties. Those will have a diameter of 2 meters each. And I forgot to paste in the areas. So there is that. All right, so the results that we're going to retrieve is right here: water surface elevation, main channel depth, the average velocity of the cross section, and the Froude number of the entire cross section. So more on that later. Let's go ahead and add the culverts now. Actually, did we even save the geometry yet? File, save geometry data. Okay, we haven't yet. So I'm going to call this no culvert. That's been saved. Now what I'm going to do is go File, Save Geometry Data As. Instead of No Culvert, I'm going to call this Alt-1 and click OK. Click on Inline Structure, and then let's see here. Click on Culvert. We're only going to have one culvert group. The shape is going to be circular. The diameter is going to be 3 meters, so that's pretty huge. The distance to the upstream cross section, 5 meters. Culvert length, 10 meters, because remember the side slope was 0. And then let's see, entrance coefficient loss, I'll go 0.5. Manning's N for both top and bottom, I'll say is 0.013. That's typical for concrete. Depth to use, bottom N. I mean, we'll just say 1 meter, I guess. I'll just say 0. It's the same Manning's N for both top and bottom anyway. And then depth blocked, 0. And then here is that 81. This is the invert we're going to be using for both upstream and downstream ends of the culvert. All right, down here we specify the number of barrels. So for this first alternative, it's only going to be one barrel. And I'm going to say that is at cross-section station 14, both upstream and downstream, which is centered within our cross-section, which is a total width of 28 meters. That's all I believe I need to do there. So if I click OK, boom, here is a preview of my 3-meter diameter culvert, just one barrel through the inline structure as you're seeing. If you don't see it, you may need to just kind of like readjust, move, or resize your inline structure data dialog box. All right, so that's cool. I'm going to close that. I'm going to File, Save Geometry Data, and then I'm going to go File, Save Geometry Data As. I'm going to create a new geometry file, call it Alt2, click OK, then click on Inline Structure. We're going to modify the culvert here. So we did this to sort of save some clicks. We don't have to, redefine some of the properties that are going to be the same for all three of our alternatives. Now we're going to have a 2.5 meter diameter. We're going to have two barrels though. Let me double check everything else here is correct. Yep, same invert, same Manning's N roughness, but instead of just B1, we're going to have B1 and a B2. Now the cross-section stationing, I'm going to set at 12 and 16. So it's still centered on 14, but we obviously need some room. So there's that. That is ready to go. So I'll go ahead and close, File, Save Geometry Data. And then for our third and final alternative, File, Save Geometry Data As. Now we're going to go Alt-3 for the name. OK. Inline Structure. And then I'm going to click on Culvert. And then instead of 2.5 meters, it's going to be 2 meters. Everything here looks good. Down here in the barrels, I'm going to add a B3 now. So let me delete the existing cross-section stations. I'm going to go with 10.5, 14, and 17.5 for the B1, 2, and 3 for my alternative 3. Okay, here they are in the diagram. Clearly, they're 2 meters in diameter. You can tell they're 2 meters tall. And then, yeah, the width is a different scale than the horizontal scale and the vertical scale, but that looks good. So let's close that. File, save geometry data. Okay, done with the geometry. The flow data will be much simpler. I'm going to be using steady state flow for this model. So I'm going to go to Edit, Steady Flow Data, and then I'm going to have 3 separate profiles. I only care about the third profile, which is going to be the largest. This is going to represent the 100 year. But for PF1, I'm just going to say is NCMS. PF2, the second profile, will be 15 CMS, or metric. And then the third profile will be 20 cubic meters per second. I'm also going to name these. So I'll go to Options, Edit Profile Names. The default names of PF1, 2, and 3 are right here. I'll call PF1, I'll change that to, actually, let's call this 2-year. So 2-year. And then PF2, I'll call that 10-year. And then PF3, I'll call that the 100-year for the 20 CMS scenario. It's this 100-year, 20 CMS scenario I'm most interested in. Click on Reach Boundary Conditions. Earlier I mentioned it's a 1% slope, so just let's go ahead and use that for our normal depth downstream boundary condition. I'm pretty sure that we're going to be dealing with subcritical flow, but we can check that anyway. Therefore, we don't need to set the upstream boundary condition. Okay, and File, Save Flow Data. I'm going to save this as 10-15-20, just as kind of a reminder for the 3 different flow rates in CMS. Okay, so that's saved. Let's close it. Time to run the plan and get some results. So let's go up to Run, Steady Flow Analysis. And we have 3 different, well, really 4 geometries, but Alt 1, 2, and 3 are the ones we're actually going to be testing. And then we only have 1 steady flow file. Let's run it on subcritical, and let's do this one at a time. Look at the results, and then finally start working on the HEC RAS controller. All right, so File. I'm going to save this plan. I'm just going to call it Alt 1, and then click OK. And then also Alt 1 here for the show ID. That looks good. Click on Compute. Let that run. Okay, that's done. Same thing, let's create a new plan called Alt2 and then use the Alt2 geometry. So save the first plan, and then let's save a new plan as Alt2. Okay, and then yeah, Alt2 is what we'll call this. And then I'm going to change the geometry file to Alt2. This is the 2-barrel at 2.5 meter diameter. File, save it first, and then we can compute. Okay, so that's done. Let's finish up here with the third alternative, save plan as. Then let's go with Alt 3. And for the short ID right here, it's asking me to type it in. We'll just use Alt 3 anyway. It's a short enough plan name as it is. And we need to switch geometry to Alt 3 and definitely save it and compute. All right, so that finished up. I'm going to close. We should have some results now. So let's go ahead and check those out. I'm going to first go up to View and Cross Section. So what we're seeing here is Alt 3, and we're only seeing the 2-year water surface elevation. Let's toggle on all 3 water surface elevations, and then we'll look at the profile view, some table data, and then finally get to the VBA. Options, and let's see, profiles is what I want. So here are the 3 profiles. I'll click OK. Boom. Now we see the water surface elevation for the 2-year, the 10-year, and the 100-year. I'm going to switch over to alternative 1 and 2 now, which has 1 and 2 different barrels. So Options, Plan. I'm going to toggle off Plan 3. Here's Plan 2. Okay, I've got the alternative 2 view right here for the cross section. We see we have our 2-year, 10-year, and 100-year water surface elevations. And also we can toggle up to different cross sections. So let's see, where is plan view? Over here in the geometric data editor. Let's toggle open this cross section results again. Then we have water surface down here at the downstream end, which is river station 0, river station 50. Here is the inline structure. Obviously the water surface elevation increases, the depth increases, and then this is river station 100. Let's go ahead and use river station 100 as the cross section of interest when we compare the 3 different alternatives, 1, 2, and 3. Number of barrels, 1, 2, and 3. Okay, I've got alternative 1 right here. Now it's open. So we have 2-year, 10-year, and 100-year water surface elevations with the alternative 1 geometry showing here with 1 culvert barrel. All right, now let's take a look at the view water surface profiles. So what we're seeing here is the 2-year, 10-year, and 100-year water surface profiles. This is for alternative 1, for the 1 barrel option. If I click on plans, let's check out alternative 2, and boom, the water surface elevations are a little bit lower for all 3 flow rates. And then finally for plans, alternative 3 and okay. Looks about the same. I think it was a little bit lower. I think I saw the lines move down, but pretty close between alternatives 2 and 3. With regard to water surface elevation and depth, we're also interested in fluid number and velocities. Speaking of which, let's go to view and then profile summary table. So in this table right here, I said we're interested in these numbers, are specifically reach 1 and the cross section at River Station 100 right here. I don't care too much about flow rate, critical water surface, energy grade line. The parameters I'm interested in are right here: water surface elevation, the maximum depth, average velocity, and fluid number. So let's go ahead and create a custom table within profile output table. So let's see, start with standard table 1. That looks good. I'm going to go to options, find table. I'm going to double click to delete. We don't need the minimum channel elevation. That's sort of like the invert value. Let me move this over here. Water surface elevation, that's the first one we want. In fact, let's see. Critical water surface elevation, no, no. Okay, you know what? Let's just find them all. So the next one we want is maximum channel depth. So let's search for depth, maximum main channel depth right here. So column 2 and double click. Okay, next up, I want velocity. So this is going to be average velocity across the entire cross section, which is this last record here, column 3, double click, and then column 4 is the last one. That's going to be fluid number, and that's for the entire cross section, not just the main channel. So double click, and we're good to go. 2 decimal point precision is probably close enough, but we could increase that if we want. And okay. All right, so here is the revised table. And then I don't care too much about 2-year or 10-year, but I do want to see all 3 plans here. So instead of all 3 profiles, let's go to options, profiles, remove the 2-year and the 10-year, okay, and then options, and then plans. Let's toggle on all 3 of our plans. And now we're looking for this data right here. So I'm going to highlight it, come back over here, and these are the numbers paste that I want to actually see here in return from my HEC RAS controller. So it's a lot of work to do manually. It's a lot of work to set up the model, but once we get the controller running, hopefully you'll be sold on the benefits of writing the script in VBA and using the HEC RAS controller. For the time being, I'm just going to keep these numbers down here, sort of as a reference. And I'm also going to copy the alternative number, so 1, 2, and 3 for our 4 different variables. All right, so this is the target that we're going for. We're going to be populating these cells. Let me go ahead and file, save this particular Excel file so I don't forget, and save it as a .xlsm, and then I'm just going to call it controller browse. I guess I'll put it on the desktop for now. That's fine. All right, so what we're going to do next is go up to the developer tab and then click on Visual Basic. And then let's see, I've got a few different Excel files open. This is the one I want. I'm going to go Insert Module and then double click that module. Okay, so I'm now writing code in Module 1. Go to Tools, References, and then what I'm going to do is include the HEC RAS 6.6 reference. Include whatever HEC RAS version that you're using. So let's see, 5.0, 6.4. I think did I already include it? Oh, no, it's right here at the top for some reason. Boom. All right, so that's checked on and okay. Okay, so first I'm going to paste in and explain the code that doesn't work, but what I would like to have work, and then make this small modification, show you the code that works, we'll run it, and then we'll call it done. All right, so what I'm doing is I pasted in a subroutine called main. And let's see here. This is going to open up the project, but it's called project 2. Right. I'm also going to display the HEC RAS GUI. That's what con.goRAS does. This is the line right here that actually opens up the project. And then this is the line that instantiates the HEC RAS controller object. We got some variables here. So what I'm doing is these are the 4 different HEC RAS ID variables. I'm calling them variable IDs. There's 4 of them, so the array is size 4. It says 3 here because it starts counting at 0. And then the water surface elevation is RAS ID variable 2. The depth is RAS ID variable 4. Velocity is 23. Food number is 49. These are the 4 variables that we added to our custom table right here. So these 4 columns right here, 2, 4, 23, and 49. So now we're back. And now what I'm doing is I'm going to loop through each plan. So the plan names were called Alt1, Alt2, and Alt3. So I'm going to reference that plan just using the I integer variable. There's also a J integer variable. I is what I'm using to represent the different rows. So I'm going to be looping my results through rows 6, 7, and 8. We'll see this row result used a little bit later when we're actually printing the results to the worksheet. And then if I scroll down here, I am setting the current plan. And then what I'm doing right here is running the computation. In fact, there's a chance that running the computation is what's throwing me off. Let me comment that out and give that a shot. And right here, I am setting the variables. And then right here, I'm actually getting the data. So we have, let me kind of work backwards here. Output underscore note output. This is the function that's going to return the value of the variable. So what I'm doing is I'm looping through all 3 alternatives. And then within each alternative, you can see right here, right here, J, I'm looping through 4 different variables. So J from 0 to 3 is the 4 different variables. Variable ID is going to be assigned right here. And then if I scroll over, actually, make this a little bit wider. Here we go. So this is the entire line. I'm passing in river ID, that's river A, reach ID, which is reach 1, node ID, which I've set to 5, and that is the node index for cross-section 100. So that's the cross-section we're interested in. By the way, this node ID, I determined it was 5 using the node index function. So it's commented out now, but earlier in my development, this was the code that I was using to determine that node ID. So here it is. I basically passed the river ID, the reach ID, and then the river station name as a string, which was 100. And then this printed out in the console window as 5. So that's what's going on there. Let me just comment that out again. Okay, back to our equation. The UPDN is not used for cross sections. And then we have the profile ID that is set to 3 because we only care about the 100-year data, not the 2-year or the 10-year. And then variable ID, that is going to loop through our 4 different variables, our HEC RAS variables, which was, I believe, 2, 4, 23, and 49. 49 for the fruit number. Once that data is recorded into this variable, it's printed directly onto our results worksheet, which I need to make sure that that worksheet is named results for this to work. And I'm setting it to the row and column, and then here is the value. I think I might have to type dot value here, or maybe that's only for when I'm getting the data. Okay, let's go ahead and see if this works here. So I'm going to click on the reset and save. I need to remember to name this worksheet. Yeah, it's called sheet 1 right now, so I'll call it results. Okay, so that's good. I think we're ready to rock and roll. So these are the target cells for the subroutine to print the results from HEC RAS into. Pull this off to the side here, and then let's see. So save. Okay, so I closed HEC RAS, and now I'm ready to run the model. Let's see what happens here. So I'm going to just click on run, and then boom. Okay, so yeah, I thought this might happen. What's happening here is it's stuck on alternative 1. Even though I switched the plan, it looks like it's recording the same alternative 1 values for all 3 alternatives. That's not what I want. It looks like it's getting the alternative 1 values correct, though. Of course, what I'm seeing down here was rounded to just 2 decimal places, so that's encouraging. Now, this is what I encountered in preparation. In fact, let me go ahead and try it one more time, but this time I'm actually going to run the simulations. So it's reset, save, and then let me clear out the numbers here, and then let's go ahead and run it. So run the simulation. This is going to run through each alternative. This is alternative 1. This is alt 2. It even says alt 2 and alt 3 right here. So that looks good. Yeah, it's still just printing out the same information. I could have been making some silly mistake, but I'm going to show you guys what I did to work around this. Basically, what I did is instead of opening up the project one time and then looping through the three different alternatives, what I'm going to do is loop through the alternatives and then open and close the project, setting the alternative right as soon as I open up the project. Okay, so here comes the incoming code. Select all, delete, and then paste what I have prepared. So as I mentioned, I'm defining the three different plan names, Alt1, Alt2, and Alt3, and then I'm looping through those plan names. And then after that, I'm creating a new controller, opening up the project, there it is right there, and then performing the other tasks that we were doing previously. All right, so let's go ahead and one last try, see if this works for us. So I'm going to delete out these previous values. So let's go ahead and run it, the revised version. And it looks like I'm rerunning the simulation. That was alternative 1. This is alternative 2 now. And then finally, alternative 3. It looks like it was printing in the background. And boom, here are our results. We successfully created a Culvert in a 1D steady flow simulation. And then we obtain the results here for 4 different critical variables: water surface elevation, depth, velocity, and fluid number. And then finally use the HEC RAS controller to retrieve those exact same numbers and paste them into our Microsoft Excel worksheet.